So last week we dealt with some binomial, or not binomial, no, that's the other class. We dealt with some within subject data. And we had this within multivariate. At the end of class, we actually created this thing within multivariate.stan. I'm actually going to open up just the within.r to start my session here. Oh, no, I had a session open, so I'm going to close my session. So now, double-clicking this, we'll open up our studio in a new session. We'll set the working directory to where we just were. Ooh, how?
You want to set it to that, not to the one you
Remind.
sent?
Pardon me? Yeah, well, I'm just going to show, because a couple of you actually weren't here last week, so I thought I'd quickly go through this, showing, well, now that I've opened up our studio, I'm going to open up that last multivariate file we created for within multivariate. And I'm going to walk through that quickly because it will set up what we're going to be doing today. So the way this STAN model was sort of structured, it was expecting data in. We were imagining, well, we actually applied this general idea to two scenarios. One scenario where you had data from each of several people in each of two conditions, so repeated measures design. And we actually restructured the data before we gave it to Stan, such that we computed what the intercept per person was and the effect per person was. Another way we did it was that we actually just imagined that we had two sort of scores per person. One would be, say, a verbal IQ score, and one would be a nonverbal IQ score. Regardless of the way both examples involved the idea that we could have a matrix of data, where each row in the matrix indicated the person that the data was associated with, so rows indicate the cases, and each column was sort of a measurement from that person on a variable. And what we are interested in is looking at, sort of, for each of those variables, where is its mean, how sort of variable is it from person to person, but then also what are the correlations amongst the various variables. So we'd have a parameter, so if we had k sort of measures, k columns in that data frame, that matrix, we'd have k means to want to talk about. We'd have k variabilities, so within each column there's a variability of measurement from one person to another. And then we have a correlation matrix of k sort of things that could be correlated with one another. So this correlation matrix ends up being expanded to sort of a k by k, and you get all of the correlations. So if there were 3 measures, you get the correlations between 1 and 2, 1 and 3, and 2 and 3. There was some new stuff that we dealt with that was usually in our model section we just start with talking about our priors and then our generative model. Here we actually have a variable being defined first. We're saying there's this thing called Z that's a k by k matrix. You have this happen when you're just going to have sort of, you need to define an intermediary variable. We can't talk about, when we have a scenario where we've got a bunch of means, a bunch of variabilities, and a correlation potentially between these measures, we're in the world of using a multivariate normal distribution. In the multivariate normal distribution, you have to give it the means, but then also the covariance matrix. And here we're just talking about the variance of each thing and the correlation amongst each of those things. So Z is going to be the covariance matrix that the multivariate normal wants. So Z is just sort of an intermediary variable. It's a deterministic consequence of what is sort of sampled for sigma and rho. So we define it at the beginning of the model block, and then it gets sort of defined here as being a function of these two things. Rho and sigma combine together to create this thing z. And z and mu, in turn, are used to talk about a multivariate normal distribution. So going through the generative part of our model, we're saying that this is the first time we dealt with loops in the sort of model block. What this is saying is sort of for each subject in the list 1 through n, so n being the number of subjects, model that subject's data, so the row of data that is corresponding to the subject that we're talking about. So first time it runs through, s is going to be set to 1. So it says model the first row as multivariate normal with mean depending on what the value of mu is and a covariance matrix z. And then loop back, set s to 2. Then it will say the second row in the y matrix will be modeled as multivariate normal, etc., until you get to the final row in the matrix. And so you're saying that each row is sampled as multivariate normal.
And y is a predefined structure, yes?
Yep, that's way up here. Yep, we defined y as just a matrix, an n by k matrix. Yep, and the actual way we gave the data in, so this was, actually we had it as our example model 4. And I can use my nice little model 3. Yeah, we talked about model 3. So we had data in a data frame such that we had 2 columns, val1 and val2.
Okay, so yeah, you just created.
We just created a matrix.
A matrix of 2 variables
In R
for
itself.
subjects.
Yeah.
Okay, gotcha.
Yeah. So when you do this, you can do inference on the correlation between variables that are measured in each of multiple subjects. And one thing about this model is that it's saying that each observation from a person is, each sort of set of observations from a person is defined as this multivariate normal. But it's actually rare that we just get, say this were the original case where we had 2 observations, verbal IQ and nonverbal IQ. It's rare that we actually have just 2 numbers measured from a person. If you actually, well, as you guys know, verbal IQ and nonverbal IQ is a composite score. You've actually done something to go from the raw observation of the person to that verbal IQ scores. It can be helpful for improving the sort of statistical precision of your inferences to actually not bother creating that composite score outside of your model, but actually reflect that each person might have a set of scores that combine together to create that composite score. So the idea there is that that composite score, is it a sum usually? The sum of all, or is it a mean? I can't remember IQ.
You sum it, but then you scale it.
Okay.
Yeah.
Well, even if it were,
Anyway.
so usually a sum, when a score is a sum, it actually is equivalent to a mean in that it's just a sum without having the divide by n part, and that divide by n just scales it. So it's when you're talking about sort of a sum variable, you can think of it as also a mean variable. So what we're going to talk about next is hierarchical models, which is sort of a variant of the multivariate case where you actually have many observations per variable of interest. And obviously there's measurement noise from one observation to another. That's the reason why you create that composite score, is to average that measurement noise out. But it can be useful to give your model all the raw data and let it see what the magnitude of measurement noise is. and that will help you have more precise inference. It also makes you can also make much cooler, more complicated models if you take into account the raw data. So that's where we get to for today's data, which is I sent you this hierarchical.zip. So if you open it up, you see a whole bunch of files. Hierarchical 1 is what we'll start with. So I'm going to double click that. That'll open up a new session of RStudio. It'll set my, remind me later. It'll set my working directory, and it'll open up the file. I'm going to pull the file out just so I can see everything a little bit more nicely. So I told you that we'll use that you should install the tidyverse package. That's just because I discovered it. I'd heard about it, but I hadn't really realized that it was useful. But it is actually only like moderately useful in that it just makes it so that instead of having to type library dplyr, oops, and library reader, and I'll spell library correctly, and library, what are the other ones? Stringer is one that gets used sometimes, library ggplot2. Instead of having to type all of those and install all of those every time you've updated things, the same person is the same author of all those packages, so they've created this sort of meta package that combines everything so that it loads everything together. So we'll run that, and it gives us a little sort of flag here. In fact, I'm going to make that fairly big, that it's loading all these other packages.
What's the RStan options?
So that's next. That little bit, if you load RStan, it immediately prints out this message. Here's the RStan package. And it says, for execution on local multi-core CPU with excess RAM, we suggest running these two things. So what I've included is this first thing. What that actually does is it means that every time you compile an RStan model, it actually also saves a copy of the compiled version as a file, such that if you close down the session, come back the next day, and run things again without modifying that file at all, it'll check the file to see if it's been modified at all. If it hasn't been modified, it will just use the already compiled code there. So that's useful to just always put in there. So we'll run this and tell it to start compiling the model. While it's compiling the model there, I'll just show you some of this data. Let's see, what will I open it with? Open with Text Wrangler is a good one. So I'm just opening it with a text file reader that opens very slowly.
Do we need to be doing this?
No, I thought I'd just show it to you here. Why is this? Okay, I'm going to open it with, what's the default? TextEdit. Okay, so this is the file. This came from, oh, that's number 2. No, I'm going to open up number 1. Okay. So this is the file. Let's see, can I zoom? No. Format, font, size.
Bigger.
I guess. Oop.
It was on there for bigger and smaller under styles.
Oh, okay, just plus. Okay, so this is a CSV, comma separated. It's got a header row here. ID, condition, and RT. So if I look it through ID, I see lots of 1s, and then eventually I'll see 2s and 3s and 4s and 5s and 6s. So this is data from an experiment looking at multiple people. Each person has lots of observations. The observations, this is long data format. You have many rows per person. This condition column, if I look in it, I see lots of A's and then B's and A's and B's and A's and B's. And critically, it looks like each person has a bunch of A's and a bunch of B's. And then finally, the last column, RT. Well, I made this data to sort of emulate the type of experiment that goes on a lot in my lab, where we measure human reaction time in different conditions. And because human reaction time is a really noisy thing, we measure it a bunch of times in each of the conditions that we're interested in. So I think there's 100 observations for each person in each condition. But we could turn this data into what we had the other day in the first example, where we just had a single value for each person in each of two conditions. By using our dplyr skills and computing a summary, collapsing everybody, so grouping by ID and condition, and getting mean RT per person and condition. That would give us just two numbers per person, a mean for condition A and a mean for condition B. And then we could use that code that we had from the other day to talk about that as a sort of multivariate outcome. However, that would be throwing away information that could be helpful. So a different idea is to say that there is some mean. So for each person, that person has, if you recall the original way we did it the other day, was we said, okay, there's an observation in condition A for person 1, an observation in condition B for condition 1. And so we said, let's recharacterize that as the center difference parameterization. So each person then had a center point, and each person then had a effect, basically, a difference score. Here we're going to say the same thing. Each person has a difference, an intercept, and each person has an effect. But once we've given each person their intercept and effect, we then say, okay, let's sample 100 observations from a normal distribution with that center and with the center plus the effect to get to A and the center minus the effect to get to B. So I'm going to start actually doing this in the drawing. All right. So we had the other day ID, and let's just call it V1 and V2, just measurement 1 and measurement 2, or condition 1 and condition 2. Actually, probably should stick with A and B. So yeah, all right. Measurements in condition A and measurements in condition B. And we converted that. So if we had person 1, they had some number there and some number there, and person 2, they had some number there, some number there. We converted this A and B to intercept effect parameterization. So they got a number there, another number there. So each person still has two numbers, but we're sort of reparameterizing it.
Sorry, the intercept was the midpoint.
Yep.
And the effect is the difference between them?
Yeah. Yep. So if you imagine a graph of each person's numbers, they have measurement in A and measurement in B. If it were something like that, whoops, then these two values would reflect sort of this distance and this distance, respectively, whereas this value reflects the distance to the center of the two, and this delta reflects the sort of amount by which you'd have to go from this center point to get to either one, so the magnitude of this difference. All right, so that's how we had it before. We went from the AB to intercept effect. We're going to do the same thing this time, except that once we have, we're never going to actually, so last time we had the data in as just a single number here, a single number there, and we simply computed this other sort of parameterization, this other way of reflecting the data. This time, we're actually not going to compute anything. We're going to have our model express that there's some number for each person, some intercept and some delta, that when you take those two numbers, so I'm going to say, I'll say for person 1, they have I1 and delta 1. What I'll say is that the observations for person 1 in condition A, so person 1 in condition A.
Mind squeezing up a bit?
Ooh, yep, thank you. Are distributed as some normal where the mean for this person's observations in 1A is their intercept plus the effect. I'm going to put a question mark here just for now. And then the data for that person in 1B is normal intercept minus the effect.
How do you, like the intercept and difference, is
Mhm.
it based on the average of all of your scores?
Aha. So we haven't talked about what we're sort of modeling these two parameters as. So what we're actually going to do is say that the set of, what's the symbol for set again? Anybody know?
Oh, this long?
Yeah.
Hmm?
Like
Just
neon?
square brackets, isn't it? Or
Oh,
I'm thinking what you're thinking.
So
Yeah,
as in a
it's
set
set.
of,
Use it for
a
set.
set
I
of
think
two
it's
values, if it's just a vector,
Yeah.
I thought it was just square
Okay.
brackets.
I'm just gonna do,
It's
so,
squiggly
Yeah.
the set
brackets.
I1, I2, ... to IN. So the set of all these observations.
And those are all the observations for the one person.
Yeah, but that's
Well, no,
Or-
the number here is the person.
It's the person.
So
okay.
person
Okay.
1's intercept, person 2's intercept, person 3's and n's intercept is, these are going to be distributed as a normal distribution. So there's going to be a mean for this distribution. So I mu, and there's going to be a variability for this distribution, I sigma.
So just to be clear, the mean of this distribution is the grand mean of all data, essentially.
The mean of this distribution is reflects the
Like an average-
population from which our sample is drawn. It's the mean intercept for the population.
Mhm.
So if we were to go out and observe the intercept for everybody in the population that exists, then take the mean of those intercepts. That's what I mu is intended to reflect. And the variability of one person's intercept to another is captured by this I sigma.
So, but in our data set, one person's intercept could still be based on, like, didn't you measure them 100 times?
Mm-hmm. But if you imagine that each of those 100 observations in condition A and B get turned into a mean,
Right.
and
the intercept is the
it's the center
Midpoint of
point
the
between the mean of those two.
It's the mean of the means, and this is the
It's a lot
population.
of means of means.
Yeah, no, exactly. Yeah, that's why they call it hierarchical, because sort of there's multiple levels of the data.
So you take, for one person, you take the means of all of their reaction times for condition A, all the means for other reaction times for condition B, and then you take the midpoint between those two, and that's what's being entered as intercept 1, and then
Yeah.
you do the same thing for okay.
Yep. Now, we won't actually have to compute those means ourselves. We actually give it the raw trial-by-trial data, and it will automatically figure out what intercept values would be best. So what I've expressed here is that each person is going to have an intercept, but we're going to model, this is still part of our generative model. We're still saying that each of these people's intercept, or the population distribution of intercepts, follows this normal distribution with these two parameters then that we want to do inference on. So we want to know where is the overall population mean for the intercept, and how variable are people from one to another in their intercept. Now that's on the intercept. We would do the same thing for the effects, delta 1, delta 2, delta 3, delta n. And again, we're going to say that each of the effects we observe from each person are drawn from a normal distribution of delta values with some mean, delta mu, and some variability, delta sigma. And we're interested in, like, what is the overall population mean for the effect? And how do people vary from one another in the population in the magnitude of the effect that they have? So, just like last time, we started out with a model that had these two normal distributions. And we at first modeled them as independent. And then we realized, oh, but we can actually have a correlation between these two values. So it could be that somebody with a high intercept also has has a large effect, or alternatively, somebody with a high intercept might have a small effect. So since that complexity to the data is possible, and indeed there are many cases where it's demonstrably the case, and it's relatively simple to to account for that complexity in our model by modeling not two independent normals, but a multivariate normal that has a correlation between, you can do inference on the correlation between those two properties. So let's take a look at the R code. Sorry, not R code, the stand code. So if I go back to my session, in theory the stand model has compiled. I'm going to open it up though. Hierarchical stand. So I'm going to pull it out so we can look at it. So there's a few things that are going to be different. Critically, if we look down at our generative model, we'll see some lines that are very similar. We've got that same looping over each subject and getting a multivariate normal. We've got a rho in there, a mu in there, a sigma in there. Okay, those are nice. But there's a bunch that's different. So let's start from the top. It's expecting the data to come in that same long data format that I showed you before, such that you can tell it how many total trials there are. So that's like how many rows in the whole data set there are total. How many within subject predictors there are. Now, with the data that we just showed, where it's just conditions A and B, condition is the predictor. So there's only one predictor going I've made it so that we can actually flexibly accommodate any number of predictors, and the next example is going to have two predictors with an interaction between those two predictors, so that this same code will handle both situations. But for now, nx is 1 because we just have condition as a predictor, A versus B. And S is you give it the number of subjects that are in your data set. So once you give it sort of the numbers of the things of interest, you then can start giving them those things. So S is just going to be a vector, the labels so of each observation. What subject does that observation belong to? So if we look at our data, so this observation belongs to person 1. This observation also belongs to person 1, etc. So it's just this column of 1s and then 2s and then 3s that we'll be giving it for that thing called S. This is expressing that you don't actually need this part. It's just kind of a check. Say that there has to be at least one person, and the numbers are supposed to go from 1 to ns. So if you had numbers in here that didn't correspond to the sequential 1 through ns, or it had numbers outside this range, you get an error, and that would help you know that you screwed something up. But this part is just saying you're going to find integer numbers in there, no decimals, no negatives, and it's a vector of length ny. X, well, I'm gonna jump to y. Y is also a vector of length ny. I could have done real and then put this ny on the right side of the sort of named object here. That probably would have worked just fine. I just happened to know that this needed me to put it in this format, whereas this was okay with me saying vector ny, and I'm used to putting it as vector ny. So this is the outcome column. So it would be the RT column here, all the RTs for all the trials. And X is going to be a matrix of the within subjects predictors. Now it's an ny by nx matrix, so there's as many rows in the matrix as there are observations for the data, and there are as many columns in the matrix as there are within subject predictors. Now we actually only have one within subject predictor, so it's a matrix with this many rows, but just one column. So that's what's going to have the numbers where we had before, like negative 0.5 and 0.5.
Sorry, so is it just like can you explain what it is again?
Yeah. So previously, remember when we did the predictors, say we had two conditions. We had to say, we had to create sort of a list of numbers that coded, okay, for this observation, if it was condition A, put a 0.5 there. If it was condition B, put a negative 0.5 there. This is that list of numbers. It's expecting in this list of numbers. For this example, it's something that has as many entries as there are outcomes. So each outcome has a condition that it came from. But there's only one column in that because we only have one predictor. This code, however, flexibly accommodates more than one predictor, and that's what we'll do in the next example.
So X is like a list of what condition it was,
Yeah.
and Y is like the list of the observations.
Yes. Yeah. So Y is the outcome, X is the predictors, sort of the within subject predictors, and S is the thing that labels what observations come from what subject. So having looked at this data, I'm actually going to pop us back to the R code, hierarchical1.r. So we've already run this bit. Stand model is compiled. Let's actually do this bit. So we'll read in the data using reader. It says parsed with column specification. The ID column is an integer. Condition is a character. RT is an integer. All right. So we can actually just look at the first little bit. Should look exactly like what I have in my text file. Since we're using read underscore CSV from reader, it comes in as a tibble. And to demonstrate, if we wanted to say, just get a sense of how many observations there are per person and condition combination, that's what this little bit here, get the count of observations per person and condition. So we use the pipe to group by, and we group by person and condition, and then we summarize, and we use the n function, which just counts how many sort of rows there are in the data frame as grouped by person and condition. So it's going to count for each combination of person and condition how many observations are in the data set, and then it'll just spit it out to screen. So this just shows the first few rows, but demonstrating that for each person, it seems that there's 100 observations in each condition. Now, we had before, if we wanted to, so we want to make sort of a column out of this condition column. So condition right now is this character A and B. We want to make it so that we've got that negative 0.5 and positive 0.5 to be our sort of numeric indicator variable. I had you guys do that by hand previously using like if-else and things like that. There's a trick, though, that I hadn't taught you yet because it's a little bit longer to do when you just have one condition, one predictor to be dealing with. But the next example shows you how it's, or has an example where you have many predictors. So this will be faster in that case in terms of just how much code you have to write. So the way this trick works, first you have to turn whatever predictors that you're interested in using. So we're interested in using condition as a predictor of RT. You have to turn that column in the data set into a factor. So that's done by saying, okay, well, starting on the right-hand side of the equals, get the condition column within the data frame, and supply it as the only argument to a call to the factor function. Factor simply grabs what's inside that column and returns a factored version of it. What does a factor mean? Does anybody? So we haven't talked about it too much because it's not, I guess we just haven't needed to until now. A factor is whenever you have a bunch of like a column of characters, but there's like specific levels in that column, so A and B, lots of A's, lots of B's. You can turn it into a factor, and R will know that that's not just a set of characters, that is specifying levels of a variable. So we want to convert. Oh, right. So that's going to factor will spit out a factored version of its input, and we're just going to overwrite the column condition with the factored version of the column condition. Oops. Another thing to do this trick, you need to ensure, at least to do the trick whilst achieving the center difference parameterization that I've taught you guys so far. For some reason, I have this set. There's a faster way to do it. If you open up hierarchical 2.r. I'm going to pop it out, bring it over, and I can do it side by side with no side by side. Okay, so I've got hierarchical 1 and hierarchical 2. You'll notice hierarchical 2 is going to look a lot like hierarchical 1. Indeed, there's the same sort of headers down here. So if I click trick to get the condition contrast matrix, it's mostly the same except for there's a thing here, set default contrast to center diff. So I'm going to copy that bit from hierarchical 2 and overwrite lines, the ensure any columns line. All right, so now you should have, I'll close this bit to make it bigger. Now you should have options, contrasts, and all this junk.
Why are you doing Helmert contrasts?
Helmert contrasts are what that center diff is another name for that center versus diff parameterization. And it'll mean that when we run this next thing, we'll get something that will convert the condition column into the numbers that we want of -1. Well, I previously had you guys doing -0.5 and +0.5. This will do -1 and 1.
I thought we couldn't do -1.
You can. It just means that you have to
multiply.
Yes. Yeah.
But why is it doing the
I don't know why the default is -1 and 1.
Okay.
I don't know why.
So it's just making sure your intercept is at 0.
It's making it so that the two conditions are reflected as a negative value and a positive value equidistant from 0, so that you have the ability to talk about an intercept and a difference.
Is it gonna automatically take care of that whole divided by 0 point? Or
Yes. Yep.
Oh, okay.
Yep.
Okay.
So if I actually look at the head of MM, so the first little bit, I didn't run the options bit. Options, and then run all that. Okay. It is actually a matrix that it's spitting out with two named columns. One column called the intercept, and if you actually, will it print the whole thing out? No. But if you were to actually look in that column, that's all ones. That's because the way this works is it's saying what conditions get an intercept, and all the conditions get an intercept in their calculation. And this column, it's called condition 1. That 1 at the end is just to reflect that it's being turned into a contrast. It's not the condition labels. And that will be -1 and 1 in that column. -1 for the first level of condition and 1 for the second level of condition. So that's been a lot of work to actually get out what we were doing before, which was just hand coding -1 and 1 in there by using if-else. But it's going to be a lot easier when we get into more complicated models. Having created this thing MM, that's what we're going to supply as the value x. That's the matrix of within subject predictors. So it's saying each trial has an intercept value, and then either -1 for one condition or +1 for the other condition. So we can package this for Stan, and I'm actually going to tell it to run. I think I sent you with iter equals 200. I'm going to take that out so that it just does the full. probably a good idea to make your computer do the full parallel version of this, but I have 8 cores on this machine. You probably have 4, unless it's Christiane. You have 8 on yours? No, you do. It's the 15-inch MacBook Pros all have 8 cores available. Yeah. So while that's going to run, because that
got rid of the iteration line, right?
yeah,
Okay.
so that it uses the default 2000. Oh, I didn't run this first bit. And actually, I'm going to just walk through this first bit again. We've got NY. Well, that was supposed to be just the total number of trials, so it's the total number of rows in the DAT data set. And X, we can just ask how many columns are there in this model matrix that we just created. Now, when I described to you the data, I said NX was just going to be 1. That's because I didn't want to tell you yet that this X matrix will actually have 2 columns, one that's all 1s to reflect the intercept, and the other one that's the thing of interest, which is the difference score, or the difference between the conditions. So we're going to say NX is the number of columns in the model matrix, which is 2. The number of subjects is the number of unique labels that it finds in the ID column. I happen to know that those IDs go from 1 to, how many unique IDs are there? 20. So I happen to know that those labels go from 1 to 20. A quick trick that is actually worth you guys writing down is to, if you weren't sure that these were sort of the sequential numbers from 1 through the total number of people that you had, if you have, say, a weird, even like a character string that identifies each person, a nice trick to get the sequential numbers, get numbers that are sequential that label each person, is to first turn it into a factor, and then turn it into a number. So the nesting here is such that it will get the data in the ID column. Whatever's there, it turns into a factor. And whatever that produces gets immediately turned into a number. That's because when you have a column that's a factor, say I had, we had the example up here, taking the condition column and turning it into a factor. If I were to immediately turn that into a number, if I had as.numeric up here, everywhere it saw an A, it would put a 1 because A was the first level of the factor. And wherever it saw a B, it would put a 2 because 2 was the second level of the factor.
And the assignment is simply based on what unique value it comes across.
Yeah, it's
in descending order.
yeah. So it's alphabetic order. So it finds A's and B's in this column. It calls the A's 1 and the B's 2.
Okay.
If I were to then convert it into a number. So that'll give us our unique but sequential subject numbers, no matter what is in this column. I should have had that in there for you guys ahead of time. X is our model matrix that we just created. And Y is, of course, the RT observations. Now, if I'm giving it just the raw observations, or what I've taught you to do more recently is to scale the data so that we can put some sort of simple default priors on it. But I haven't done that here. That's because I've tried to simplify our lives by doing the scaling in Stan itself. So I'm going to run this and tell it to sample. Do that yet? No. Okay. So while that's running, because that's going to take a while, I'm going to look at the stan file and walk you through sort of how things are done. So what do I mean that I told it to do the scaling within stan itself? Well, first of all, you guys can delete these 3 commented out lines. That was me exploring something. So when we used to, well, what I'm doing here, I'm saying that before, so I'm creating a new section called transformed data. You can use this to do any transforms on the data before stan does anything. So the transform that I want to do, I want to create a new thing called YZ. Basically, I just copied this line and I put it down here, and I named the thing differently. So instead of Y, I'm creating a thing called YZ. And I'm saying in YZ, put the result of this computation. And this is the computation that we used to do outside of stan to rescale things. So I said, every entry in Y, subtract the mean of Y, and that will yield a big list of numbers. And for every entry in that list, divide by the standard deviation of Y. So that's creating this thing called YZ. That is then what I'm going to be using in my sort of expression of the generative model, which means that we can use those default priors. So saves a little bit of time outside of stan if you're going to be reusing this stan file a lot.
And that is, sorry, is that just transforming the reaction time values into z-scores?
Yeah. Yep. And additionally, we had some headaches when we were using these scaled, when we did scale things in R, did the inference in stan using the default priors and got samples. We then had some headaches trying to convert those samples back to the original scale of the data. So we've got a new section here called transform data that achieves the scaling to the z-scores. Now at the very end, we're going to have a new section called generated quantities that undoes that scaling for the parameters. So there's 3 parameters that sort of are ones that need to be rescaled. So for the mu parameter, there's a mu parameter in the model, and that specifies the population mean on something. Actually, I'm going to walk through the model itself, and that will make what's going on down in the generative quantities a little bit more straightforward. So I told you that each person is going to be modeled as having, having their own, so person 1 is going to be modeled as having an intercept and a effect, and so all the observations in their A group is going to be modeled as a normal distribution with a mean determined by the combination of those 2 things and a variability that we had a question mark on. Ditto 1b was going to be, again, a normal distribution with a mean combining the intercept and effect in the opposite direction, and then a question mark for what the variability was. We'll still get back to that. So each person is going to be the combination of their respective intercept and effects, and those intercepts and effects themselves are going to be sampled as normal distributions with some correlation between them. So what about this question mark? Well, this question mark is saying sort of how much noise is there from a given individual in the observations we make of that individual in a given condition. A very popular thing is to, another way of phrasing this is to say, what is the sort of measurement noise? So let's call this one sigma. So a very common thing is to say that sigma is common not only from one condition to another, so there's the same amount of measurement noise in one condition as the other, but sigma is also common from one person to another. So we are saying that the intercepts differ from one person to another and the effects differ from one person to another. So we sort of model each person as having each of these things and a distribution, a multivariate distribution of these things across people. But sigma is just going to be one value that's the same no matter who you are and what condition you are in.
If you were doing a mixed design, would you just have different sigmas for each comparison that you make between participants?
Nope.
No?
Very common is to not do that. You can, though, but that's not a complexity we'll necessarily get into. So that's where this parameter is coming from. It's saying that there's trial-by-trial error, or measurement error, and it's just a single thing. So everybody has the same measurement error no matter who you are and no matter what condition you're in.
What if something happens in the one condition?
Sorry? We can certainly model condition effects on measurement error and even variability of one person to another in measurement error. So you wouldn't expect, say...
Like spill coffee difference.
Yeah. You wouldn't expect like a scale to have different measurement error across different people. But you would expect something like reaction time to have different measurement error. And indeed, it's known that young people tend to have not a lot of measurement error, and older people tend to have much more measurement error. There's more variability in how they respond. So this is a constrained model that doesn't take into account any of that complexity, but it's relatively trivial to add in that complexity and ask, like, is there a difference between conditions in the amount of measurement error? Here, this is a pretty standard hierarchical model or mixed effect model that most of the ones that you've seen published, if you've had any exposure to mixed effects models, make this assumption. So I thought I'd start with that at least. So sigma is just one thing. We're going to have a prior on it that we've seen before, sort of a log normal 0, 1. That means it's peaked at a value of 1 on the real scale, 1 being the amount of variability we just observe as noise in the data without having any predictors. That's how we define the z-score. Okay, so the next thing, mu. Mu is going to be, for each sort of predictor we have, it's the mean across the population for that predictor. So we have nx is 2 because there's 2 columns in this thing called x. One column is the intercept, it's all ones. One column is the coding of what condition that trial is from, either A or B. So we'll have 2 mu values. The first one will be the population's mean for the intercept. So if I said the intercepts all vary from one person to another, but they are going to take a normal distribution. The intercept, this is going to be mu1. And the other entry in mu, because it's only of length 2, is going to be the population mean for the effect, the difference between conditions. In the same way that we have a vector of length nx, so 2 in this case, for the location of the population distributions for each predictor, we also have a vector of length nx for this thing that is new, we'll call tau, and that's the variability in the population. So tau1 will be this thing here that I erroneously called I sigma. just imagine that that's a tau now. So tau 1 is the variability of one person to another in the intercept. And tau 2 is going to be the variability of one person to another in the manifestation of this effect.
So tau's the variability from like between people, but then sigma's like within one person's own.
Yeah, yep. Sigma is the amount of sort of noise that you observe within a person, within a condition, in just trying to measure them. So much like our multivariate models before, we're going to say that sort of these things, mu's, are going to, the observations, the means, the i's and sigmas for each person are going to be sampled from a multivariate normal distribution, which might have zero correlation between the intercept and effect, but they could have a correlation, so we'll do inference on that correlation with rho. So saying core matrix NX rho, it's going to be a 2x2 correlation matrix, which of course just has 1s on the diagonal, and the off diagonal is the correlation between the intercept and the effect. Now a new thing here is this line, SMU. This is my way of saying the subject mu. So I've said that each person, we're modeling the data as if there's some population of intercepts with some mean and some variability, but we actually observe a bunch of intercepts. This list of intercepts is what's in this matrix is the list of parameters that each person gets. So if we look here, person 1 gets an intercept and person 1 gets an effect. So for each person, we're going to have, so NS is the number of people. So there's 20 rows in this matrix and 2 columns in this matrix. So this matrix contains the model's estimate for each person's intercept and effect. So really what we're doing is we're saying that these values here are drawn from a multivariate normal distribution. If you imagine, this is kind of like what we had as data input earlier in the previous class's example. We just had a matrix with as many rows as there were people and as many columns as there were things we wanted to model as multivariate normal. So we had the single value for the intercept and the single value for the effect. So that was data as input. Now we're saying that this is not data. We have raw data in the form of this y. We're effectively modeling the intercept that the person has and the intercept that or the effect that the people have as latent variables. We could actually estimate them very well by getting the mean per person per condition and using that, but technically it's still a latent variable in that it's a sort of, we go from some set of variables which will produce this variable, which will then eventually produce the data that we observe. So walking through the model section, we have the same sort of bit that we needed in the earlier multivariate example where we had to sort of express that there's this intermediary variable z that's a covariance matrix of the predictors. So we combine the correlation that we want to model amongst the predictors with the variability that we want to model within each predictor to create a covariance matrix called Z. We express our priors on the 1, 2, 3, 4 parameters that are sort of truly parameters on which we can express our beliefs. So sigma, we'll say log normal 0, 1. That's sort of a standard prior for our variability. Tau is also a variability, so we also use the log normal. Again, sigma is the trial by trial variability. tau is the person-to-person variability in their each of those effects. Mu, we'll model that as normal 0, 1. And I told you the other day that this rho distributed as LKJ core 1 effectively means a uniform prior on the correlation between the intercept and effect. If you wanted to express sort of more credibility at 0 and less credibility at high values for the correlation, you'd use larger values like 2 or 3. Tends not to matter too much.
Question.
Yeah.
So for like when you're doing multivariate models, because like I mean in this case you only have it's not as relevant, but because you're making matrices, right? That could have like multiple mu's.
So yeah, so the mu is a vector that in this case has 2 entries.
The intercept and the
Yeah.
effect. So your priors then, you're setting one prior.
I'm saying that each entry. So this actually, I could say mu1 is distributed as that, and
Okay,
mu2 is distributed as
specify.
that, or something slightly different. If you actually had different priors for each column, you didn't want to use the standard priors, you could totally do that.
Okay.
Yes. I've been lazy, scaled the data, and am using default priors, in which case you don't, if you fail to specify which entry in a vector you want the prior to apply to, it applies the same prior to each entry in that vector. So sigma is only one thing, so it just gets this prior. Mu is 2 things, each of which is going to get this prior. Tau is 2 things, each of which is going to get this prior. And rho is more complicated. All you need to know is that this expresses sort of a uninformed, uniform prior on rho. So having expressed the priors on the sort of population level parameters, we have this section next, which looks like what we used to have for the multivariate. We're iterating over something. We're iterating over subjects. So for each subject in the list of 1 through ns, we express that subject's entry in the matrix mu as distributed as multivariate normal with a mean of mu and a covariance of z, where that covariance is the combination of the correlation and the variability that we wanted for each parameter. So we'll loop over each subject and assert that their sort of parameters for the intercept and effect should be multivariate normal. And finally, having this thing called SMU, which is a matrix, we can express the generative model for all the data at once, all the raw data. And that's by saying YZ. Again, we're going to use the Z-transformed version of the Y. And we're saying it's normal. It's got sigma measurement noise. Standard deviation of the normal is sigma. And then this bit inside, I'm pretty sure we had that at different earlier days. Did we? No? This bit just does the math to figure out, okay, given this subject's values for the intercept and effect, and given the contrast matrix that we made, so for each row in the contrast matrix, get the subjects that correspond to that row's values for the intercept and effect, and also get the contrasts that are associated with that, so whether it's which condition it's in, basically, and multiply them together to figure out what that condition's mean should be. So if this were participant 1 and they had an intercept of, I don't know, 2, and that participant also had a effect estimate of, I don't know, 0.5, this would have, this for a row in the model matrix that had a coding to say there was condition 1, or whatever the first condition was, there'd be a +1 and in the intercept column and a -1 in the, what do you call it, the effect column. So that +1 would be multiplied by the mu to get the intercept value for that participant. So +1 times 2 is 2. And the -1 would be multiplied by the whatever is in the effect column for that participant. So -1 times 0.5 is -0.5. And the rows dot product bit will make sure that those two numbers get combined. So 2 minus 0.5 to make it so that for condition 1, they always get a 1.5 in that column. Whereas if it were condition 2, it would be a 2.5 in that column, I guess. Yeah. So this just goes through and basically makes sure that each of the subject's intercepts and effects is applied in the manner that we originally intended, where the for all the data in condition 1A, it's normally distributed with this way of combining the data, and for all the data in condition 1B, it's combined in this way, and we don't have to mess with looping over participants or anything like that. This just does it kind of automatically. If you understand the generative model, or the ideas that I've expressed in the on the paper here, you don't super need to understand this part. That's a little bit sort of what might be considered optimized for the computer and not for the human. So this simply expresses that the observations from a given person in a given condition is sampled from a normal distribution with a mean corresponding to the whatever combination of intercept and effect is for that person, plus a variability of sigma. So now that we sort of have a feeling for the parameters in this model, I can explain to you what this generated quantities is doing. So we've got this thing sigma that represents the trial by trial measurement error. Since we have scaled the data, sigma is scaled to the z scale. So if we want to get it back, we have to create something that we'll call sigma unz. And if we got to the, well, the way to return to the scale of the data is to multiply by the standard deviation of the data. Ditto, we've got this other variability parameter, tau. Yeah, it's mine. Sorry. Oh, I can actually turn it off, can't I? Yes. I taped over my home button, so I couldn't but yeah. Okay, so tau is another variability parameter. So for the variability parameters, all we have to do is multiply them by the standard deviation of y, the variability of y, to get them back to the raw scale. So tau unz is equal to whatever tau is times the standard deviation of y. Mu is a location parameter. So in addition to multiplying by the standard deviation of y, for that very first entry in mu, which is the intercept, we have to add in the mean of y, because we artificially shoved the overall intercept of the data, the mean of the data, to 0 by scaling. So if we want this first entry to reflect the mean of the data on the data zone scale, we have to add the mean of y just to that first entry in mu.
Out of curiosity, from way, way back in like the second class, the reason we're going to the Z distribution is to make our priors, the default priors, easier to type. But why not simply say the prior is 1 times the standard deviation and just leave everything untransformed?
Yeah, that'd work too.
Oh, okay. Is it just
No,
that
no
this
good
is-
reason.
Okay.
It kind of makes, like, if you, so what he'd suggested is,
That's going to be plus the mean of whatever sigma is going to be.
I actually have to think about that a little bit. It might actually be harder than I initially thought. Because I'm thinking about this, how to make that so that I don't think you can do that. I'll follow up separately with a demonstration why, but I actually don't think you can do that. I think you have to do it to the data.
So you can't simply just linearly transform.
No,
the
because I don't think this. I think you'd have to do something in here. Like, this is pretty straightforward.
Yeah.
Times SD of y. But what would you do here?
Well, when
You can't say 0 times the SD of y because that's still going to be 0.
But that would be the mean, right? So wouldn't you just be adding the mean to that, so it's not centered on 0, it's just centered around wherever the data is?
Well, let's talk about that at another time.
Okay.
I actually think that would be slower to compute too, because you have to do some
it is quite possible
operations.
It will be slow.
Okay. Anyway, so we're somewhat acquainted with the model. We might get a little bit more acquainted by actually looking at the output of the model. So let's do that. So in theory, it's gone through, it didn't take too long, 20 seconds total on my machine for each chain. Let me go through here. I'm going to have it print out. Oh, no, I have to make my screen bigger. Print out the whole thing. So much larger output than we used to have. Well, let's look at the, so what's happened here is that in addition to the sort of main parameters, sigma, mu, tau, and rho, we actually get those estimates per person of what that person's intercept is and what that person's effect is. As I said, those would be considered latent parameters, so we can do inference for each person. What sort of is the credible values for that person's intercept, and what are the credible values for that person's effect? So this is actually kind of nice because we can actually talk about, like, if this were a scenario where maybe you were questioning with one person might have a diagnosis that should be excluded, you can actually talk about, well, what is the credible values for that person's specific data? And if that starts to sort of diverge from what the population's data is pretty considerably, you could start to use that as basis for excluding them or considering them as an outlier in your data. I won't talk about that too much. I'll just, for now, just say that you actually get estimates for each person, for each parameter in the model.
Why would I? So all my values are the same, except for my effect. The NF is, mine are all double yours.
Did I do 8 or no? Yours are double mine, so you probably left it at n chains equals 8, and n cores equals 8. Yeah.
So it doesn't actually like.
No, you just sampled even more, so your results are a little bit more precise than mine. Once you get over 1,000, it's not.
It's
not
the same
gonna.
anyways.
Yeah.
Is this standardized or unstandardized?
Okay, so the top here is going to be the standardized things.
But didn't we?
Okay.
Oh. I
At
see
the
it.
bottom
Just kidding.
is the unstandard. At the bottom is the unstandard. So you can actually see the sort of consequence of the standardization. We up above, sort of sigma was 0.39, mu for the intercept was precisely 0, which we kind of expect because that's how we define the transform. And the size of the effect on average in the population was about 0.36, whereas down here sigma is about 40, the mean of the population, mu on Z1 is 480, and mean of the effect is about 40. So if you're, it's mostly down here that we want to look at things.
Sorry, that mean of the population, that's the intercept, right?
Yep. So this 480. So the population's overall intercept is around 480. The difference between the two conditions in the population is around 40, with a credible interval ranging from about 34 to 42. So the range of this credible interval is pretty far away from 0. So I would suspect that 0 is rather untenable as a hypothesis for an effect. So you could turn that around and say, I found an effect. These two values aren't sort of super interesting. They simply say sort of how variable manifest, like this one says how variable is the intercept in the population. So it's actually fairly variable, that standard deviation ranging from 72 to 140. And this one, a little bit more interesting, how variable is the manifestation of this effect in the population? So standard deviation from about 6 to 12. If this were milliseconds, that would be a pretty, I would happen to know if that's a pretty consistent effect from person to person.
Is it small?
Because yeah, there's not a lot of variability from person to person. 6 to 12 milliseconds, whereas the magnitude of the effect is up in the 40s. So if you think about sort of the ratio of the size of the effect to the variability of the effect, it's like a nice.
Isn't the variability, the tau 1, isn't that across both groups? So it makes sense there's a lot of variability if you found an effect, like a difference between the groups?
Well, we don't have groups here. We just have everybody's being measured in two conditions, and this tau on Z is the amount of variability in the intercept that manifests from person to person. So I just happened to artificially create it to be a large number. So so this is fake data in the first place.
Right, but because we found a difference.
Remember, it's the center point between those two.
Yeah.
So it's not talking about like tau on Z1 isn't talking about the overall variability, knowing that conditions are different. Like that will be independent. The amount of variability there is independent of the size of the effect that you might find in the thing.
So if you were to explain this effect in the words, what would you say?
So these results, I'd say, here's sort of the credible interval for the mean is, I seem to be getting a pretty strong effect that's around 40 milliseconds. It's fairly consistent from person to person in that there's only about a 10 millisecond variability. This I wouldn't necessarily comment on too much. I'd just say that people are variable from one to another in terms of where their mean RT is.
And would you talk about the conditions?
Sorry?
Would you talk about the conditions?
Well, since we only have two conditions, this is the difference score between the two conditions, so that you don't need to do anything. I do have code that's going to show you something about that, but before I get there, the other thing that you'd want to talk about from this is this bit here, rho. We didn't need to scale rho because rho is just on the correlation scale, so it doesn't matter if the data is being scaled or not. But this is talking about whether there's a correlation in sort of the intercepts and effects that we observed. The point estimate, sort of the peak credibility is around 0.49, 0.5, but the range is all the way from like 0.02 to 0.77. So I might be fairly confident it's positive. I wouldn't be super confident in precisely the value that that's taking. And that's just a function of the amount of data that I have. I'm sure that if I were to record many more, so there's only 20 people in this data set. If I were to observe, say, another 20 people, so 40 total, I'm sure this would narrow up to be more confident in what the precise value of the correlation was.
So what are, for the mu and tau, and then the row at the beginning. What are the numbers in the square brackets again? So like mu1, mu2.
That just says which element of the. So we gave it a vector. Let's see. When we created that model matrix MM, and I'll say head of MM. The first column was the intercept, and the second column was the condition.
Okay.
Having done it that way, that means that when we have the results, the first thing in mu refers to the intercept, and the second thing in mu refers to the effect.
Okay.
So mu is a location parameter, so this is talking about the location of the intercept in the population and the location of the effect in the population. Tau is a variability parameter, so it's talking about the variability of the intercept, the variability of the effect.
And then within row, so when it's 1, 1, 1, 2, 2, 1, 2, 2, that's standing for what?
So row, remember row is a correlation matrix. So this is the cell number in the matrix. So 1, 1 is the upper left corner. 1, 2 is the next one over in the row. 2, 1 is the.
Sorry, what are in the.
Okay, so it's just the column number. So numbering from the upper left corner as 1. Moving over 1 is the 1, 2. Moving down 1 is 2, 1.
No, I understand that. Like
Okay.
where they fall, but like what is the actual thing that's in that?
Oh, okay. So any correlation matrix, the diagonal is all going to be 1. So you can always ignore. Whenever these two numbers are the same, ignore that. So that's 1. 2, 2 is all 1. The off diagonal, this is the correlation between the intercept and the effect.
Oh, okay. Okay.
And this is the correlation between the effect and the intercept,
Gotcha.
which are the same.
Should have labels.
Yeah. Yep.
So that.
Well, I'm going to show you. Yes. Okay. Wish it had labels. It's about to, at least for mu. I haven't coded up the visualization of the rows with labels. So let's visualize the location parameters with nice labels. So this might be something that you, well, for just 2, I guess, parameters in your model, intercept and effect, it might not be very
Nope,
parsimonious.
Still wanna do it.
Sorry?
Still
Yeah,
wanna do it.
but for the next one, it might be parsimonious. So okay, let's visualize. Basically, I just want to visualize the information that's in this table, the credible intervals for each parameter that we've done, but ideally with their names. So that's what this next section, visualize location parameters, does.
It's very long.
It is. But we'll walk through it. So we're going to talk about mu unz, so that it's on the scale of the raw data. We extract, so we've got this object post that contains all our posterior samples. This will extract just the samples corresponding with mu on z. And we immediately turn it into a data frame. And we can take advantage of the fact that we actually still have this thing mm kicking around. And mm has the names of those variables, intercept and condition. So if I run just this bit, and I say head of mu, I now have a column that's the intercept samples and a column that's the condition samples.
But the value in the condition one is actually the reaction time.
So this is again, no, this is the posterior samples for the population's mean on the intercept. So they're all around like 500, and this is the posterior samples on the population's mean for the effect.
Right.
So they're all around 40. But they're labeled now. Instead of mu on z1 and mu on z2, we've got intercept and condition. Let's do some.
What was the dim names again? DIM names?
It's just a trick I happen to know of getting the names from this model matrix. If you look at the head of MM, it actually had those names in it. So I just grabbed them and put them on the head of mu, the data frame that I created for mu. So, I ever use that? I don't believe I do. I'm just triple checking something. No. This bit is actually unnecessary. I was doing it earlier for something. It doesn't hurt though. So we're going to reshape the data to wide. Wait, no, that's not true. It's reshaping the data to long. Sorry. And I've just experienced in the past that sometimes factor levels can get screwed up. So I do a mutate here where I take what's in. I'm just going to select this bit and see what's in it. So to see what the product of a sort of dplyr chain is, you can just select all up to that point and not select the subsequent pipe. So I will run that, and oh, I thought it would be a tibble. So this is the long version of that same data set, that same table of intercepts and condition. Again, these are the posterior samples for what we should believe about where the population mean for those things are. So we got par and value as columns. So this bit just makes sure the par column is factored and has the levels that are the same as the dim names, the names of the dimension there. So that creates this thing called mu long. I actually thought that I was going to reuse mu long earlier. I could have had a just straight continuing pipe through, but I thought I was going to reuse mu long, but I don't think I do. So, but we'll leave it in there as an object that we created. Having created mu long, which is head mu long, is again another data frame, but this time instead of 2 columns, 1 for each parameter, now we have 1 column, all the parameters in a single column, the values for the parameters in a single column, but another column labeling what parameter we're talking about for that row. So further down, there's samples for the effect as well, condition. So again, that long data format that we've used previously. So now we need to sort of summarize for each parameter. So we're going to say group by parameter. We're going to do a summary. We're going to get the median for that parameter, so the quantile of 0.5, and a couple intervals. The interval from 0.025 to 0.975 and 0.25 to 0.75. So that's the 95% credible interval, the low value for the 95% interval, the high value for the 95% interval, and the low value for the 50% interval, and the high value for the 50% interval. Having computed those summaries, we then want to visualize them. So we're going to use ggplot2. For these sorts of plots, I like to actually put it so that on the y-axis is the parameter and on the x-axis is the value. This is more useful when you've got lots of parameters. Here it's not as useful. So we're going to have sort of the thing reflecting the value of the data is on the x-axis this time, and the labels are on the y-axis. And I'll just run this to show you what it looks like. So parameter, we've got the intercept and condition, and RT milliseconds. So you can see the intercept has a value at that white point, at sort of a peak at that white point. That's where the median is, but here's the 50% credible interval, and there's the 95% credible interval. The effect is way down here. The condition effect, it's around 40, and it has a very tight credible interval, so tight that if we're plotting the intercept and the effect in the same plot, it's hard to see sort of values of those intervals. Very common when you have many effects, and they're all sort of pretty low, but a scenario like this where RT is the intercept is a very large number, you can just take off the intercept entry. That would leave this plot with just one entry, which would be seemingly like a waste of ink. It'll look a little bit better for the next example.
Does this suggest that in this experiment the effect is really small? So
Yep.
You don't get
Yeah, it's small, but small relative to the intercept. And I wrote up some code for you guys. Well, I'll be using it too, but I just did this morning, that if you want to actually ask, well, what is the mean for condition A and what is the mean for condition B? If I want to see that sort of expected plot that we might have, I'll go through this quickly and we'll talk about, well, we won't have a chance to talk about the second model today, but we'll hopefully get to talk about what this is doing a little bit more next class, but we'll just show it for now. What this is doing, it's getting the predictions from the posterior and figuring out what each condition's mean should be, what the value for each condition should be. So we get out a thing called mu condition post. For condition A and B, there's a couple values. So for each sample we're getting of the posterior, we're getting out what that sample's intercept and effect would produce as condition means. And then this bit does that same summarizing and visualizing. This time a slightly different visual because we're putting, again, now more expected, the value on the y-axis and the condition on the x-axis. This is condition A. It's condition B.
Can you go back to your table for a second?
Oh.
Sorry.
Yep, there. For this?
Yeah. I have different values. Like, to the extent, like, instead of 408 for the first one there, I have 453.
Oh, no, that should be fine.
That's okay?
Yeah, that amount of. Because I've got 408 for this one, and 443 for this one.
Okay. But,
So-
sorry, but I don't understand why.
Because probably we just have slightly, like, that we
Okay,
didn't
it's a
grab the
computer
same.
thing,
Yeah.
okay.
Like, if your plot at the end looks different from this, that would be concerning. But if you ran enough iterations and enough chains, we should have similar plots. So when you want to know what sort of, you could figure out just by math what the what these imply for the values of each condition, but I provided you with handy code to.
I got an error
Figure
when I
that
tried to run that. It says unknown variable to group by A.
Well, we're out of class time, so maybe I'll come over and check that out right away. So we're gonna move on next class and talk about a slightly more complicated hierarchical model, but that's going to introduce the idea of how to use this same code for doing, say, multiple effects and interactions and things like that. Yeah. Any questions?
In terms of like, just trying to step away some big picture what this
Mhm.
means for, so the hierarchical models are used when you have multiple, or like one person does multiple conditions.
Yep, one person does multiple conditions and specifically multiple observations in each of those conditions. Now, they have benefits unto their own in terms of having that ability to see the measurement error and to take that into account when doing your inference on the other variables you're more interested in. Gives you more precise inference. There's other benefits in that, let's see, a very popular thing right now is when, say, linguistic research, you often consider, okay, people are going to differ consistently from one to another in how they react. So a person is consistent within themselves in how fast they react, but that's going to be different from person to person. Similarly, words are very sort of have that same sort of property that we can expect a given word to have. We all react very quickly to that given word relative to other words. So a high frequency word typically will engender a faster, say, lexical decision time than a low frequency word. And so you can actually treat words in the same way that you treat people. You say words will differ randomly from one another, but within themselves be really consistent across people. So whenever you have a scenario where you have both words and people, you can model what's called crossed random effects. All it means is that words have this sort of consistency within themselves, but across people, but variability from word to word. And people have consistency within themselves, but variability from person to person. Normal models wouldn't allow you to have that scenario, whereas the mixed effects model allows you to have that scenario, crossed random effects. That's really popular now. It's the only way when you have, say, a whole bunch of binomial data sort of in each condition per person. A very common thing is to say, so in this condition you have a bunch of ones and a bunch of zeros, and in this other condition you have a bunch of ones and zeros. A very common thing is to compute a proportion, say it's an accuracy thing. So I say proportion correct for you in condition A, proportion correct for you in condition B, proportion correct for you in condition A, proportion correct for you in condition B, etc. That can certainly be demonstrated as troublesome in many cases, if not incorrect. More acceptable now is to actually model the data in this way. Instead of having at the stage where you're talking about the actual observations as being normally distributed, you'd talk about them as being what's called Bernoulli distributed, i.e. turned into ones and zeros. And that solves a lot of issues with binomial data where you can have many observations per person. But yeah, these mixed effects models are pretty sexy right now because people are just, in psychology, are just learning about them and starting to use them. All right.